We will review the sites present in this chapter in order to close it, and the topic of the existing sites in 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 the existing sites. We will gather some points from both and discuss them, God willing. Last time we talked about radiation and mentioned that there is ionizing radiation and non-ionizing radiation. The idea behind this is that it knocks out electrons from the atoms, which is why it is called ionizing radiation. Ionizing radiation enables the knocking out of electrons. There are types of ionizing radiation, including photons like X-rays and gamma rays, and particles like beta, alpha, and neutrons. We discussed the topic of direct and indirect effects. I mentioned that if we are talking about the indirect effect, in this case, I produce free radicals, which result from the interactions between ionizing radiation and water. Free radicals then cause damage to DNA and the cell membrane. In the case of direct effects, ionization occurs due to direct interaction with the type of radiation. DNA occurs without any intermediary or material in the sample, and regarding this, we also talked about DNA damage. I mentioned that the effect that happens is related to several factors. If we talk about it, I have daily occurrences of DNA damage ranging from 10,000 to a certain extent. They experience damage, and I said, well, right now the merging that is happening is already the cell producing the repair enzymes that repair the damage occurring. However, if the repair does not happen, meaning it becomes incomplete or fails, in this case, it initiates degeneration or cell death for me. In the case that damage occurs and there is incomplete repair, I end up with a mutation. That's it. Mutation stimulates the possibility of developing cancer or genetic effects. I mentioned that the topic is divided into two effects, deterministic effects and stochastic effects. I said that deterministic effects are dose dependent, relying on the radiation dose, and their severity increases with the dose. I noted that the deterministic effects include erythema, skin burn, and cataract, which start to appear as a result. Well, of course, I have this, and this happens as a result of what is present, okay? I have cancer, and this happens as a result of the radiation that is present, right? Okay. There are also some specific effects that may result from the interactions that occur between radiation and certain cells. The topic may involve the release of some chemicals that could affect the cells, even if they themselves have not had direct exposure. This is a result of possible interactions that can lead to the release of certain chemicals or transmitters that are transferred to the cells. In normal cells, during the division process, they go through specific phases. The G1 phase, which is responsible for growth, the S phase where DNA is synthesized, the G2 phase, which prepares for mitosis, and the M phase, which is mitosis itself. I will find that my cells are considered. I will find that I have both mitosis and meiosis, because in this case it happens, and thus I became more. So we talked about the topic, and I said, well, the background radiation varies from country to country, and it depends on the nature of the ground in that country. For example, I have the UK, which is 2.7 menesaV per year, and from natural sources, it's about 2.3 menesaV per year. As for medical exposure, meaning people who are exposed due to tests and examinations, it's about 0.4 menesaV. Okay. Immediately, completely. The risk of cancer in the case of exceeding, or if you are exposed to levels between 100-200 MSV, is considered a significant increase in cancer risk. Now, regarding background radiation, we have all talked about it, and I mentioned that there are natural sources of radiation, such as the radon gas, that comes from the decay of uranium found in rocks, which then accumulates on the walls of homes. There is also radon coming from the ceramics present in houses and radon gas that exists in our bathrooms. The necessity of ventilation is crucial because radon represents a risk. I also mentioned that even in my food, whether I am eating meat or any food, there is a certain percentage present, and I consider it a common regional activity. Radioactive material is potassium 40. We said that in every potassium I have, there is approximately 0.12% of potassium 40 from the regular potassium present. We talked about the definitions of absorbed dose, effective dose, and equivalent dose. I mentioned that when I talk about radiation, I say that I have a bare source of radiation, like X-rays, and this ordinary X-ray comes from an X-ray tube that I control and produce. When I have a radioactive source, this radioactive source contains, as we said before, protons and neutrons within the nucleus. The imbalance between protons and neutrons is what causes radioactivity. There should be a balance between the number of protons and the number of neutrons. The imbalance is what leads to radioactivity. If I have an excess number of protons over neutrons, I will find that a proton starts to transform into a neutron, resulting in what is known as beta plus decay. If I have a neutron count greater than that of protons, a neutron will transform into a proton, leading to beta minus decay. The decay that occurs transforms an unstable atom into a stable one. This transformation process is called decay. If I have 1 decay per second, I call it a becquerel. A becquerel represents 1 decay per second. If I have a material where the decay rate is 3.7 x 10 molar 10 decays per second, I say that the radioactivity is 1 curie, which means that the activity of this material equals 3.7 x 10 molar 10 decays per second, or becquerels. So this is the term activity, which expresses the activity in nuclear medicine. Of course, I can say that I have a radioactive substance today, or radioactive material, meaning you have a certain amount in millicuries. This all represents the radioactive activity of your radioactive material. The more you increase or change the activity, intensity, and magnitude of this particular material, the more that will come out of it in a very short span of time. Is that clear to everyone? Please let me know if you have any questions. Okay, this is regarding medicine. If I am talking about radiation, or if I have emitted beta plus or gamma radiation is emitted from the nucleus. This occurs through something called isomeric transition. What is isomeric transition? It is when I have an element or a substance, and this substance, for example, the most commonly used today in nuclear medicine is called technetium. Technetium-99, you find next to the word technetium-99 the letter M, which is technetium-99M, and it is metastable. So where does this technetium come from? It comes from the decay of a substance called molybdenum. Molybdenum is the generator that contains my radioactive material that comes from the nuclear reactor at the department I have. That's it, molybdenum. The decay of another material or atom called technetium-99M means that it is in a metastable state, which is not stable. Then technetium-99M decays into technetium-99 as a result of this decay, producing gamma rays. These gamma rays are exactly like X-rays in every aspect in our properties, but gamma rays emit a single energy level, unlike X-rays. For example, if I adjust my machine to 140 kilo-electron volts or 140 kilovolts, this does not mean that all external devices have 140 kilo-electron volts, but it means that there is a level of external devices that I previously referred to as the X-ray spectrum. However, in gamma rays, I have a situation where all external gamma rays carry the same energy level in technetium, which is 140 kilo-electron volts. But the penetration power needed for shielding is the same, requiring a single shielding process. Everything is like X-rays. It's a photon, and it's just a photon. As we said, The energy of gamma photons is single energy, while X-rays come out in the form of a spectrum of energies. Now, I have a person who was exposed to radiation, so I have an exposure dose. Did all the radiation you were exposed to, you undergo absorption? No, not all of it. So, there is a part that was absorbed and a part that was not absorbed. The part that was absorbed is called the absorbed dose. We said that the exposure dose represents the charge produced in the air or per unit mass of air. I have radiation incident on a cube or a mass of air that causes ionization, creating positive ions and negative electrons. This means that ionization knocked out an electron from the atom, making the atom itself positive and the electron negative, thus forming an ion. The number of ions formed in this mass of air increases. So I have a term called exposure dose that represents the charge per kg of air, meaning the amount of charge that was formed per kg of air. A kilogram means the amount of charge that is formed per kilogram of air. When the number of charges reaches a very large number, I need to introduce a unit to facilitate the measurement process, just like I did with the becquerel. I mentioned that 3.7 times 10 to the power of 10 decays per second is easier for me to understand. The same idea applies here. The charges will be very numerous, so I need to assign a value or introduce a new unit for this matter. What is this unit? I named it to represent this value of charges. Okay, the thing is it fine? This is a standard system, meaning there is something called, okay, per kilogram, and this is a classical unit, which is the Röntgen, okay? This is a standard system, which means there is something called, it, okay. The amount or quantity or the amount that is, well, what is this in terms of units? This is the first point. So did everything happen to it? No, I have. The absorbed part is considered the ionizing gradation energy absorbed by the unit of mass, which means the energy absorbed by this person in joules, and the mass is in kilograms. Thus, the joule is referred to in kilograms, which is the gray. The gray is the SI unit, or the Central International Unit of Absorbed Dose. The old classical unit was called rad. Its name is rad, which equals 100 ergs per gram, and gray equals 100 rad. This is if you want to make a comparison between the existing units. However, this expresses that you have talked about exposure dose and discussed the exposure dose. But what type of argon absorbs radiation? Should I create a new term or a new item representing this topic? I told you we will work on what? We will work on the equivalent dose. I don't see anyone wanting to join in. We will talk about equivalent dose, which is the same as absorbed dose, but multiplied by something called radiation weighting factor. This means the type of radiation. We said that each type of radiation has a specific effect. Alpha particles are different from beta particles, and so on with neutrons. Each has its own effect. It was stated that the effect of alpha particles is 20 times greater than that of X-ray, gamma ray, and beta particles. That's why it was concluded to create a term called equivalent dose, which includes the irradiation weighting factor that you should consider. This is imposed because it represents the radiation weighting factor, which is 1 for X-ray, gamma ray, beta particles, protons, 2, alpha particles, heavy ions 20, and neutrons ranging from 2.5 to 21 depending on the type of neutrons. There is something called epithermal, something called thermal, and something called fast neutrons depending on the type of radiation. The effect will vary between thermal and something called thermal. There is also a separation based on the type, which varies. Okay, so the type of neutrons that are present. I have talked about the equivalent dose and mentioned that its unit will be the sievert. The sievert specifically represents the unit of equivalent dose, and its old units were rem. We concluded, and you mentioned that you did not consider the sensitivity type of the organs. And I said that since I have all the organs present, the tissue sensitivity factor will be significant for me. So here, he started to categorize the existing organs and assign each one a value for the tissue sensitivity factor. Therefore, if you want to calculate the effective dose, you will take the equivalent dose and multiply it by the tissue weighting factor to get the effective dose in sieverts. So these are the exposure dose, equivalent dose, and effective dose. The dose that you are measuring with your personal dosimeter should represent the effective dose, which is measured in TLD. Now, as you are aware, some equations. The slide shows you what we talked about a little while ago, which is about the amount you got based on the type. So, you calculated the amount of radiation according to the sensitivity of the organs. Did you get the effective dose? Here, the topic of tissue sensitivity factors is represented, which relates to the absorbed dose in gray. You multiply it by the radiation weighting factor to get the equivalent dose, and then multiply it by the tissue weighting factor to obtain the effective dose. The radiation weighting factor is the summation of all organs, where the tissue sensitivity factor equals 1. If you have alpha particles, their effect is 20 times that of gamma rays or beta particles. Neutrons fall within their range. Now, if you want to convert between Röntgen and rad, using this division or the equation in front of you, it's not crucial, but if you have a value in exposure in Röntgen and want to convert it to absorbed dose in rad, you can multiply or divide by 0.87. Each Röntgen equals 0.87 rad, giving you the value of the absorbed dose. Regarding the absorbed dose, 1 Röntgen is approximately equal to 1 rem, or the same relationship as 0.87. This table represents the absorbed dose for each type of radiation, showing how their equations work. The type of radiation or its SI unit is the activity in becquerel, while the classical unit is the Curie. Here is the relationship between the Curie and the becquerel. The absorbed dose is measured in gray, with the classical unit being rad, where 1 gray equals 100 rad. The equivalent dose is measured in sievert, with the classical unit being rem, and the effective dose is also in sievert, with the classical unit being rem. I have the rem. It's not very important, but it represents the amount if you are one of those people. Its unit is fine, but it indicates if you have been exposed to a certain dose of radiation. They were exposed to a certain dose of radiation, and you have a group of people who were exposed to a specific dose. You want to know the probability of cancer that might occur in this population. There are certain calculations for this, but I don't want to go into the details. If you are interested, we can discuss it later. This gives you an idea of how many people might develop cancer from a specific population exposed to a type of radiation or a certain dose of radiation. The topic of the effect of radiation depends on something called linear energy transfer, LET. If you ask, are alpha particles considered high linear energy transfer or low linear energy transfer? What about X-rays or gamma rays? Are they considered high linear energy transfer or low linear energy transfer? Linear energy transfer and low linear energy transfer. In the X-ray or the coal mine, it is called linear regression transfer and low linear regression transfer. What does this mean? It means that Jusaimat alpha are heavier than helium. A large amount of energy is lost, which is considered to have a high ionization density over a short distance. Consequently, the energy or miqdar al-energy that occurs during the transferring process is lost over a small distance or very high short level. Thus it is called high lit or high naql al-taqa al-khattiyya. While X-rays and gamma rays have high penetration power, their level of ionization is lower, so they are classified as having low naql al-taqat al-khattiyya. Of course, this topic is very important in treatment processes. So, if I come to treat a certain type of cancer now, and I use, for example, a source that gives me Jusaimat alpha or even beta particles, for instance, there are some treatments like one that involves something called lithium-90. They use it in a medical procedure known as radioembolization, which involves the precise injection of a radioactive substance directly into the tumor that is located within the liver. This technique is designed to target the tumor specifically and starts to work based on the innovative idea that it utilizes beta particles or heavy particles. These particles are able to localize and deposit their energy within the tumor effectively. Unlike gamma radiation, which would lose all its energy as it passes through the body and thus cannot effectively treat the tumor. This method is highly efficient. It is currently used in advanced medical imaging and treatment techniques such as beta CT with lutetium-177, lutetium PSMA, and lutetium DOTA. These substances are known for their ability to deliver targeted radiation therapy, providing a more focused treatment option for patients with liver tumors. The use of lutetium-177, for instance, has been extensively studied and is known for its effectiveness in treating certain types of cancer, offering a promising option for patients. Nociceptin is one of the substances used in the treatment of prostate cancer. Nociceptin is considered a common element that emits beta particles and begins to target the receptors present on the prostate, specifically the PSMA. It starts to target them and is injected into the patient using a specific technique, allowing it to reach the prostate and eliminate the existing cancer through the beta particles that are released and become localized. This is very effective. Currently, DOTA is also used for endocrine tumors, which is one of the applications that utilize high linear range transfer particles. While lutetium also emits particles, the amount is very low, but it is mostly considered. Beta particles are currently being rigorously tested alongside actinium, which also emits alpha particles. They want to use it in various applications for radionuclide therapy, or sometimes referred to as targeted radionuclide therapy. Of course, it is not considered as powerful as alpha, but it is still a particle. What does still particle mean? Alpha is considered the most highly destabilizing, followed closely by beta. Today, the applications in use do not allow for the use of alpha particles due to availability, so I use beta particles instead. Beta has a traveling distance in air of about a centimeter. However, inside the body, since it is a particle and not a photon, it causes ionization with the cells and atoms present, reducing its path or the distance it travels to approximately about a millimeter. I am not talking about air. I am talking about inside the body. Therefore, the level of air decreases as it undergoes ionization and loses energy according to the energy it emits, because beta particles do not emit a single energy level, they emit a spectrum of energies. Depending on the energy, they start to move a certain distance. As a particle, this helps with the idea of ionization or its movement, similar to how an electron moves. When an electron moves, it moves in a way called tortuous motion, meaning it has random movement and does not travel in a straight line. For example, if I told you that a gamma photon moves in a straight line,